so it's entirely based on the Prince and Links textbook, chapter 2. Now there'll be a couple of illustrations which don't come from chapter 2, but for the most part, it is chapter 2. And it's a reasonably good chapter. I mean, it's very concise, and it deals with a lot of stuff like the Fourier transform and shift invariance and all the linear systems sort of groundwork that's required in order to write down mathematics about medical imaging. Okay, and it could be a whole course, actually, linear systems or something like that. But we're going to compress it into one chapter and one lecture from this book. For those of you who don't have experience with this type of analysis and this type of math, you probably have to go through that chapter a couple of times and write stuff down and work it out to your own understanding. And the TAs and we're here to help you through that. We'll post up this lecture on the the Canvas site. So you just click on the playlist and it'll be there. So let's just review quickly what it is we're talking about. We have images, right? Is our end goal is to create a picture, much like this one here. And when you ask, well, how do we encode that picture mathematically or quantitatively? You break up that picture into voxels, and a voxel can be thought of as a little rectangular piece of the patient. And inside that little rectangular volume, you're going to assign a value, right? And that value can be displayed as a grayscale here, right? So the values in the background here are likely 0 because the MR signal from air is 0. And the values in the brain are different than 0. They are probably positive number, right? And you can see here, for whatever reason, the very pure water that's in the middle of this person's brain comes out with a darker signal, and so the values are smaller. Okay. In 2 dimensions, it looks like this. We can have 2 coordinates, x and y, and then values as a function of x and y. And in 3 dimensions, we can have x, y, and z position, and each voxel has a value as a function of its position in 3 space, right? So that's mathematically how you encode an image. And we're going to look ahead and say, where are we going with this lecture? Where do we want to be after we've looked at a lot of these mathematical tools we're going to look at? We're going to get to a place where we can think about an input to our imaging system. And this input, oftentimes a very useful input, as we saw when we looked at defining the point spread function, a very useful input is a delta function or an impulse. So it's a very bright signal that has very small dimension, right? And so that's input into our system. And then we characterize what the imaging system does with that input with this output, right? So it takes a dot and turns it into this sort of sombrero type of function in this case, just for this example. And we would like to mathematically describe how that happens with this sort of mathematical expression for the system. Like, what does the system do to this tiny dot as it's passing it through and making a picture? Okay, so that's the structure. We'll get back to this slide in detail, but this is where we're going. We want to know how to mathematically describe this thing, how to mathematically describe the output of our system, and how to mathematically describe our system. So we want to be able to write all that down and work out some details about that. So as a review, recall the closest that we have thus far talked about an impulse or a very small object that we're going to image was, for example, this stainless steel bead that we put in a CT scanner, which is a tiny little thing. And then we looked at the image created by that bead, which looks something like this, and called that the point spread function. In this lecture, it's often going to be called the impulse response function. And that means you've got an impulse, i.e. a almost dimensionless object, which is called an impulse. And then we ask, well, what does the imaging system do to that? And we talked about how when we have two beads and we bring them together, we can define resolution as a point beyond which, or if the beads get any closer, you can't determine that there's two beads there. That's one possible definition of resolution. So how do we define mathematically an impulse, right? So we could have a function that goes along the x-axis at zeros, and then shortly before the origin, it shoots up to a high value. And then shortly after the origin, it goes back down to zero. So that's like a rectangle function that's very, very narrow, right? And that's essentially what the delta function is in the limit of the width of that function going to zero. So it gets taller and taller, and it gets narrower and narrower, and that's what we're going to call the delta function. And to define the delta function, so here it is here, delta as a function of position in the plane. And everywhere other than the origin, this function is zero. That's an interesting concept, right? But anyway, and the definition of that and how it's used, it came out of physics, actually, I think, not out of math, but because it was practical necessity, right, to have a function like this. But this is essentially the definition of the delta function. If I have any function in the plane, fxy, so some kind of, cake function sitting there, fxy, and I multiply that function at each point by the delta function and integrate over the plane, what comes out is the value of fxy at the origin. That's what pops out of this integral here. Okay? And you can construct delta functions like this rectangle that gets narrower and narrower as the limit. But the net result, the way we use the delta function, is right here in equation 2.5. Okay, so that can be thought of as the definition of what the delta function is. Okay. If we look at a diagram of the delta function in the plane, you can think of it like this. Everywhere in the plane, x and y, it's zero, except at the origin where it has this value such that when you integrate across it, it sifts out the value of the function at the origin, right? That's called the sifting property of the delta function. It picks off that value and returns it. What about other places in the plane? Well, we can displace this very high delta function, in the plane, right, by just adding two constants to the argument there. If I have a mouse. This might go better. It might not. Oh yeah, there we go. So if we want the delta function to sift out values at some position, psi and eta, we can write it like this, where we've displaced this peaky thing by psi and eta, respectively, in the x and y directions. Okay, that's pretty easy. We'll get back to these forms of the delta function. This is a very important form of the delta function for computed tomography, where you sift out all of the values of a function along a specific line in the plane. And this is called a sampling cone, where we have many delta functions existing together at regular spaced intervals on the plane. And these will be used to actually sift out discrete values of our function at specific points, right? That's called a sampling function. Sorry. Down, yeah. So two functions that come up all the time when we're doing imaging are the rectangle function and the sync function. And the rectangle function is defined for this course like this. It's 0 until you get close to the origin at the x value of 1/2, goes to unity to 1, and then when you go past 1/2, it goes back down to 0. Okay, so it's 1 in dimension x and 1 in dimension height. Okay, that's the rectangle function. And that's extremely useful for things like masking stuff So if you want to multiply a portion of the image by a mask, you can just move this rect function around and multiply it. Yes?
So the definition for the rectangle, do you have it undefined for x equals a half?
I don't know. Do you know? I think it's yeah.
Because usually I've seen it like pretty much the top line is correct, but the other
Yeah,
is
yeah.
zero otherwise.
It's otherwise, yeah, 0. And you're asking, is it defined at a half as somebody like 1/2 or
With
something
this
like that?
definition form,
Yeah.
we don't have to define.
There is no definition. Yeah, let's call it 0 at a half.
Okay.
Okay. So it's useful to mask things, and you can obviously change the dimension of the rect function by putting a scale value in here, like bx, would make it larger or smaller. And we can shift the origin. The sinc function, and we'll find out a little bit later that the Fourier transform of this function, of the rect function, is this function. It's the sinc function. And you don't necessarily understand that yet, since we haven't covered the Fourier transform. However, this function oscillates like a sine wave, and it decays away like 1/x. Okay, so it's something that oscillates and decays away from the origin. That's called the sinc function. And its algebraic equation looks like this. It oscillates as sine x, and it decays as 1/x. Okay. Two very important functions, and they turn out to be Fourier pairs. They can also be defined in 2 dimensions, and it's a simple extension in that now you have basically a square in the plane that is non-zero inside the square, 0 everywhere outside. And the sinc function in the plane can be described as the product of 2 sinc functions everywhere in the plane, such that you have a central peak, and then as you go away from that peak, it rings down in amplitude. Okay. The other thing we're going to use a lot of are complex numbers, and these turn out to be absolutely essential / tremendously useful for both CT and MRI, which are the 2 imaging techniques we're going to look at today. But in particular MRI, because MRI what encodes where something is in the patient is actually the phase of the signal that's coming in. And so understanding how you can manipulate phase and writing down equations where you're changing the phase of the signal is extremely useful. And it turns out that complex numbers are great for that, because you have both a magnitude and a phase defined for any complex number. So the magnitude of the complex number is just the length of the vector in the complex plane, just through Euclidean math, right? And the phase angle is defined as the arctan, right, of the y component over x, or the imaginary component over the real component. And we'll see that this is tremendously useful, and that'll become evident in a minute. Also, complex numbers have this constant. It's I if you came out of physics and things, J usually if you're in electrical engineering. And it's defined essentially as the square root of -1, such that when you square J, you get -1. And if you're multiplying 2 complex numbers that are sitting in the complex plane, and this one has a real component of 3 and an imaginary component of +2, J in the y direction, this number has a real component of 3 and -2J in the imaginary or y direction. You multiply those 2 numbers together, you just multiply it mechanically, just as you would 4 numbers in parentheses, and this comes out to a real number, which is 13. And this is where it all comes together in a way, where this equation here is, if you rumble around in YouTube and look at math things, it's often stated as the most beautiful equation in mathematics, right? And a lot of major mathematicians think this is the most beautiful relationship between numbers and mathematics. And it has a very interesting look to it, right? When you first look at it and it's introduced to you, it's like e, you know the function e to the x, right? So that's the function such that when you take its derivative, it's actually the value of the function. Okay, so that's a very special kind of function, right? And so when you raise e, Euler's constant, to the power x, and you take the derivative, you get that relationship. Well, what the heck does that have to do with cosine and sine? Like at first blush, e to the x, and thinking, well, I'm taking derivatives and it's e to the x. Why on earth would this be true? That you have, you know, this relationship between theta with the cosine and sine and e, right? So the only way I can make sense of it right off the bat is say, well, both of these functions, this one on this side, you take its derivative, you get the itself, right? So that's like an infinitely differentiable, repeating value kind of derivative thing, which is kind of the same for cosine. When you take its derivative, it has sort of a cyclical behavior to its derivative, right? So you get negative sine and negative cosine, and then it just goes around and around and around as you take the derivative over and over again. But the cool thing is that this very compact notation here, e to the j theta, gives you a unit vector in the complex plane with angle theta, right? And we call that basically a phasor. It's just the only thing that it's telling you with the theta values where that phase is. Another interesting thing about this equation, you know, if you're trying to figure out why are these things related, is if you look at just the Taylor expansion of cosine, say, right? So you have at the origin is 1 here, and then as we move away, you subtract a bit off, x squared over 2 factorial, then you add a bit more x, you know, 4 factorial, and you subtract some off, x to the 6 factorial. And we're going to expand it around the origin. It'll be this polynomial, you know, for as long as you want to write it out, right? So that's the function. And interestingly, when you're trying to create this series, right, you ask, well, I got to alternate my signs and everything's even, right? So if you have -1 to the n, it just flips sign between terms, right? J to the n, on the other hand, we get it flipping signs with every even value of x, right? So it's a very, you could say, oh, it's just this convenient little notation. We stick it into this series and it'll get, when I square it, it's negative. When I take to the 4th, it's positive. When I take to the 6th, it's negative. So that gives you the alternating relationship in this series. Anyway, lots of things to think about with Euler's equation. Okay, so I mean, this is really dry. It's just like introducing mathematical tools. It's like saying, you know, this is a hammer, this is a screwdriver, you know, this is a drill, right? But you need these things. So now we're going to look at another concept called plane waves, because we use these a lot, or we think about these a lot. So let's look at this. I'm sorry it's so tiny. Can you see that at the back? But so here's a function in the plane, s xy, defined over the plane. And that function is sine of 2 pi mu naught x plus mu naught y inside the argument of sine. Okay. So as these numbers cycle through and get bigger, we're going to oscillate with a sine wave with particular frequencies. So these numbers, mu naught and u naught, are the spatial frequencies for this plane wave, right? These are the independent variables. X and Y are just positioned in the plane. So let's see what happens when we change mu naught and u naught. So let's set mu naught to 1 and mu naught to 0. Sorry about the notation, but that's what they use in the book. we'll get to a better notation soon, in that these spatial frequencies will be kx and ky, which is a lot easier to say. Anyway, so if mu naught is 1, then we have 1 cycle of a sine wave across this unit dimension in x. So this could be, say, 1 centimeter from left to right. And then with mu naught equal 1, that's like 1 cycle per centimeter. And so when we move from left to right, it goes through its peak, goes back through 0, goes through a trough, and then back. So it's 1 cycle of the sine wave, right? If I set it to 2, then the frequency of that sine wave increases, and I just go through 2 cycles over 1 unit of x. Same thing with 4, I go through 4 cycles. So I can set the frequency of my plane wave just by changing the value of mu naught in this formula, okay? Interestingly, when we start changing both the mu naught x and y, then essentially what happens is it looks like the plane wave is just changing its frequency in the plane and rotating into a different direction, right? And so that angle, this angle or the direction of this plane wave will be proportional, obviously, to the ratio of these guys, these frequencies. And so the angle increases as we increase the oscillations in the y direction, right? And the spacing between the troughs gets narrower as both numbers go up, right? So that is essentially how we create plane waves, okay? And we've just done it with a sine and with 2 wave numbers that give us the frequency as we move in x and the frequency as we move in y. Going back to the Euler equation, right? We can have a complex function in the plane, right? This function, where we have a frequency as a function of x and a frequency as a function of y. And it will give us essentially a unit amplitude function, but just the phase of that function is defined by essentially the k, or the wave number in x and the wave number in y, right? And just as we looked at this function just now, right, and we can compose using Euler's equation an equation for this phasor by adding the cosine and adding the sine with a j in front of it, and then we get this very compact notation for how you describe a phase change as a function of position in x and y, okay? Now we're going to try and quantify with some mathematical expression what it means to take a function that is existing in space. So let's say it's a actual picture on the wall, or say it's the wall, right? And then we're going to take a photo of it or a picture of it with our imaging system. And so the true function is what's on the wall. And that's going to be, if you know it ahead of time, that's this thing, f(x) and y. It gets modulated or transformed into an image by our system. And so the way the notation they use in the book for that is they just, this script S, right? They just say, we're going to take our input, and the system, the script S thing, is going to make us an output, which we'll call gxy. I've just changed this script S to this for these slides because I didn't have one of these in my. So we're going to look at this is a definition of what it means for a system, this script S thing, to be a linear system, okay? And if it is linear, it has some properties that makes it very easy to cascade systems together or add systems up independently. And so if you can describe your imaging system as a linear system, then for example, each component of the system is described as a linear system, then you just cascade those together quite easily to make the whole system. So if you want to put complex parts together to make a bigger system, it's very convenient if they're linear. And those of you who've taken algebra, it's exactly the same concept, right? It means that if you submit a single image, right, which is this function here, and this single image is the sum of many independent images. Okay, so we're going to sum all those images together. And when we sum them together, we'll use an individual weighting coefficient for each image. We'll go to create one total image that we submit to our system, our imaging system. And then out the back comes G, X, Y, right? Once we've added up all those things together. If this system is linear, we can also do the following. On each one of those images that was the composite used to make this total image, if I just submit that to the system, each image, right, and get an output for each one, then I can sum with the same coefficients those outputs, and it will give me the same value. Okay, so it's the definition of linearity, right? Is that it doesn't matter if you sum up the pictures first and submit it to the system, or you use the system to transform each one of those individual pictures and then sum them up. You get the same result in the end. And so here is that picture again, where we have some input. We have the system, our imaging system, that is going to take that input and create an output. Okay. So what mathematical tools do we have to actually write down what this is, what this will do to our signals, right? This system. What we're going to use is a concept called the impulse response function, or the point spread function, to describe what this system is doing to our input. So let's assume we have an input. This doesn't look like a delta function, it looks like a big old ellipse, but we'll say it's a very small dot. It's a delta function in the plane, and it's a delta function displaced at some value in the plane itself, right? So the plane is here, this would be y, this would be x, and we're going to push that delta function around, push it through the system, and see what comes up, right? So we have, essentially, when we do that for all values of psi and eta, right, we get a whole set of these impulse response functions. And if it depends, where this delta function is, if it's up here, right, with a certain psi and eta, and I get a different function, hxy, that comes out as a picture, that produces a different picture, then that system's not called stationary. It actually doesn't have shift invariance, or that this point spread function changes as the position of my input changes. If, on the other hand, I limit my field of view in my image such that it doesn't really matter where in that field of view I put a delta function in, I always get the same amount of modification of that delta function, or blurring, or whatever, then it's called shift invariant. And so here's our impulse response, right? We're going to define basically what it means to have this system as when I stick a delta function in, like for any theta and eta, I get an output function, which is my impulse response, right? And so I have essentially two independent variables. What we can do then to write down what the system is for any image, right, that I put in here, I can define what the output image will look like. Well, this is let's not call this an image, for any input function, right? So it's signals coming into my system. All I have to do is integrate over, essentially, for a specific point in the plane. When I want to say, well, what does my image look like at this point? I look at my impulse response at that point, right, and integrate that impulse response over the entire space of my image, right? And so I would have to do that individually for each XY, and I would have a different H for each XY if the system changes from from point to point, right? If we can assume that H is constant as a function of position, right, then we can make a really nice simplification, right? We don't have this huge dimensional function. We have a smaller dimensional function, which is 2D, and we just shift that same function around the plane to create our output, okay? And so that basically has now, where I had 4 independent parameters here, now I basically have a 2D function in which I'm just shifting its values as I move around the plane. And so now when I put that in for my impulse response function, this actually becomes a very tractable problem, right? In the sense that I have my input that I'm taking a picture of, and then I essentially, for each position in the XY plane, I just convolve it with the same function H, right, over the input dimensions, right? So this function doesn't change. I just shift it and do the integral, right? So I shift it by XY and then do that integral. This integral, it turns out, has a definition, right? This, what we're doing here has a definition, and it's called convolution. Okay? And it has a, you know, if you want to say what does this mean? This means I'm convolving my input with my impulse response function. That gives me my output. And convolution is used all the time in imaging analysis and image reconstruction, and is now used all the time in deep learning, right? So I think probably all of you have looked at convolution in the context of deep learning, because these convolution neural networks have been so amazingly successful at processing pictures to recognize things, recognize objects, or classify objects, right? So if you want a 99% chance of being correct to identifying a cat versus a dog, that thing is usually a convolutional neural net that does that, right? Yeah.
So you have a delta function and you put it through a system and then you get an impulse response.
Correct.
What is that system? Have you defined that system yet? Yeah.
That system is this integral, right? That's how we're modeling it. Physically, what is that system can be many, many things. So that system could be, I have a CCD array and a lens, right? And then I ask, so I have an object, it goes through the lens, it gets focused on the CCD array. The lens will do some kind of distorting. The CCD array will do some kind of sampling, right? I have to write down, how do those things translate into being this point spread function?
So the impulse response, which will change according to the system that you.
Yeah, exactly. So if my impulse response, for instance, in computed tomography, when I take a picture and I'm going to use that to reconstruct a final image, each picture I take has a source for the X-rays. And let's say that source is a very, very small dot, okay? So with that very, very small dot, it still blurs the picture because it's a finite source, right? And so I would get some impulse response for that. And now I say, well, you know what? I need more X-rays I'm going to make that dot bigger. So I get more X-rays, but they're coming from a larger area. Therefore, this impulse response changes. So you need to write down a new one or measure a new one to accommodate that, right? So that's for each imaging system, that's essentially what you're doing is writing down, this function. And we assume, ideally, that you can measure it in a few places and it will be the same from position to position in the field of view. Not always a great assumption, but ideally that's what happens. You can measure it, and the way you measure it is you put in a tiny object, right? And then you measure the object, that tiny object, with one way of taking your picture, say with the very small X-ray source. And then I measure the dot with a bigger X-ray source, and the image looks blurrier, right? And so I get a new value for the point spread function. Okay. All right, and so measuring these things for imaging systems is part of the engineering tasks that when they build a new scanner, they need to quantify like how good it is by looking at these particular functions, and it's usually this thing. Right? So convolution, just as a definition in 1D, as a pictorial definition, I mean, this is essentially the arithmetic definition. It looks like this, right? Pictorially, just in one dimension, if I'm convolving F with G, G looks like this. The way this goes is you flip G around, right? That's where those negative signs in the integral come from. So you flip G around to look like this, and then we're going to pass G across F. And at each displacement across F, we'll multiply the two functions together and plot the integral of that product. Okay, so remember here, this is a product. Here's the function. Here's our point spread function. We're integrating over these two variables. So here's the negative. Remember, we flipped it around. It's the negative. And we're going to drag this function across here. And this is what it looks like pictorially for these simple functions. When they're not overlapping, right, you get 0 for the product. So the convolution gives you zeros if they're not overlapping, because the multiplication is 0. When they start to overlap, we get whatever the value is. Like if this height is 1, then we get this value as the integral, and you plot it. And then here, if they're totally, completely overlapped or most overlapped, we get the peak, and then as this one moves along here, we get this thing here, and it decays away. So the convolution of this rectangle and this sort of sawtooth, bit of a sawtooth, comes out looking like this, right? Yep.
So here you put G, right?
Yep.
So in the previous slide, isn't it opposite? Shouldn't H come after F?
This is H convolved with F of X.
Put F, right?
Yeah. Sorry, this actually, I think this should be flipped around, right? Here and here. Yeah, I think this I think it's I think this should be flipped around, right? Yeah. Yeah. Well, that's true. They're totally similar. It doesn't matter which way you do it, right? As we'll see a theorem later that it just doesn't matter which direction it's in. Yeah. Okay. So convolution in 2 dimensions, and this was pulled out of a deep learning, like, public website or whatever. Here's the website down here. So if this is a convolution kernel or h of x, the way you do it in a 2D convolution is you pass that kernel across the picture, add up the products of the picture and your kernel, which is your h of x and the picture, and then that gives you a single value where this thing is centered, right? Where the kernel is centered. And this kernel, or h of x, can just raster along here. So if you go to this website, it has like animations of how this is going. And so, you know, if this looks like this is like some Sobel operator, so this is doing a derivative or something in here. But, you know, if this was a large number with smaller numbers out here, that would be a kind of a blurring function that was being passed across the image. So this is a big deal now in deep learning, is learning coefficients for these little kernels that you can store and will, you know, will give you information that you can learn to distinguish, say, a cat and a dog or whatever you're trying to distinguish. Anyway, for us, we're looking at convolution in the sense of our point spread function convolving our input to give us our final image. If the system that you're dealing with has multiple stages, then, and each one of those stages can be measured and codified with its own point spread function, right? Then for a linear shift invariant system, if things don't change as a function of position and it's linear, then you can take your input, pass it through the essentially convolution in your system of the first stage. The output of that goes to the second stage, right? And then you get your image. So you can imagine there's, you know, multiple stages in many imaging systems, right? There's first, you know, receiving the signal itself, and then sometimes there's a denoising component, which, you know, can be a second box here. You're going to do some denoising. And so if it's a linear shift invariant system, it doesn't matter which one of these you do first, right? And you can put them together just by taking the convolution of the two of them with each other. And now you have one stage that is you know, the H for the whole system, right? Similarly, if the system is broken into two parallel pathways and they're both linear shift invariant, then you can just add up, just by the linear property, you just add up the outputs to get G. Okay. Oftentimes it's in many imaging applications, the point spread functions can be separated into two independent point spread functions for the different directions. So if I have, say, some detector array and it has a different resolution in one direction, say in X, than it does in Y, I can break that up to two independent processes where I have an independent point spread function for X than I do from Y. And so the total output of the system can be computed with these sequential 1D processes in that. If I have my input, and so for each value of Y, so for each row, I can just run my point spread function in X across that, do that convolution first, right? So Y here is just a placeholder. Just says for this Y value, we're going to run our blurring or our convolution in X first. And we do that for every Y value. And I take the output of that. The only thing that's been blurred here is the values in X, and stick that in as the input to the next stage, which is figuring out what the output from the Y is for every X. And that gives me my final image. Okay, so I can do those two things independently in one dimension. And that's in the days where signal processing used to be computationally expensive. It was very good to do things in 1D, right? Because you could do them quickly as opposed to doing things in 2 dimensions. So here's an example of a, you know, input, or this is our image, our God-given truth image in X and Y. This is after convolving with a blurring function in X. And so you see the whole image looks blurred, but if you look at particular places, like at the top of the head here, that edge is not really blurred because we've only done a convolution in the X direction. And then after the convolution in the Y direction is done, then the entire image looks uniformly blurred. So now we're going to look at the Fourier transform. This is the thing that, you know, you should know this thing really well, this transform. It has many myriad of uses, and just working with it and trying different functions here and what the Fourier transforms are, it's a good exercise. I've also put on, I think in this week's module, there's a book by Bracewell who, you know, there's a bunch of books on just the Fourier transform, right, and all of its implications. But the one book that I found very useful was this Bracewell book, and I think there's 6 chapters there. So if you read the Princeton Links book and it's not making that much sense or something, you need some help, you can look up the same topic in this 6-chapter PDF and for the Bracewell. And so, well, let's just look at the parts of this equation. We got this phasor. Remember, we're now pretty familiar with what this thing is, right? It's a unit vector that spins around in the plane, right? So it's just a phase shift. This is our input value. So we're of the function, it's a 2D function, and we want to find out what is its Fourier transform. And then this is the Fourier transform. And the Fourier transform, remember, is a function of spatial frequencies. Okay, it's a plot of amplitudes and phases actually at different spatial frequencies, given we started with this function that is a function in space. Okay. Interestingly, the inverse Fourier transform looks almost identical to the Fourier transform, except the integration is done in spatial frequency space. So here's our Fourier transform sitting in the spatial frequency plane. There is no minus here, right? That's the one difference. But when you do this integral, you get the original function back, right? If this is its continuous Fourier transform. Okay. Looking in 1D, if we look at that formula and ask, well, how are we going to compute this thing with this phasor? So here's a function that's in 1 dimension. So it's g of x. It's just, you know, some oscillating function is in 1 dimension. And when we take this integral, remember what we're going to do in the Fourier transform for a specific spatial frequency, we've moved to this kx notation from mu. So for a given spatial frequency, we set that constant here in the integral. And we're going to compute what the coefficient, the Fourier coefficient is at that spatial frequency. So set that number to what you want. Let's set it to, I don't know, 20 cycles per millimeter, right? So you put that number in here and then you perform this integral. And so this function is an oscillating function at that frequency, and we integrate the product of that function with our input, right? Looking at it in coses and sines, that, you know, using the Euler relationship, that comes out to this. And so now we're multiplying our input function with a cosine wave at our specific frequency kx, and then doing that integral, right? And we're doing the same thing with sine, but it's got a j in front of it here. You can kind of see how this is going to go, right? If this, say this function has a lot of similarity to cosine, you know, 2 pi kx, x, if they travel together and the products are high, you're going to get a large number for that. So if it's similar to cos to this thing, you'll get a large value. If it's quite different, then that integral is going to just integrate out to 0, and there won't be a large value there. Okay, so here's the, say, cos 2 pi kx. So anything that kind of looks like this function, such that they don't cancel each other out, you will get a positive value, right? And anything that looks like this function, like this gx, you'll get a big term here, right? So what do these coefficients look like? Well, we can look at it as, for specific examples, when we create a function using Fourier analysis. So this function here, it's basically a square wave, right? So it isn't a simple cosine wave or sine wave. It's something else, right? It has very sharp corners, right? A simple cosine looks something like this, or a sine wave looks like this. Kind of like a square, but it doesn't have those really sharp corners, right? When we take the Fourier transform of this thing, when we look and say, what are the amplitudes of the composition of this function, right, at different frequencies, we find that there's finite values here, right? And these are the relative amplitudes at these specific frequencies. Another way to look at this is I can create this function by summing up these functions. So I sum up a simple harmonic that's at the primary frequency, and then another one that's at 3 omega, and another one at 5 omega, etc., with a specific pattern with decreasing amplitude of these higher frequencies. And as I do those sums, when I sum in this one, it looks like this, gets closer. Sum in this one, it looks like that. And if I just keep going to infinity, basically, I finally get to my square wave. And so these amplitude values are the values of the Fourier transform of that function, right? That's what the Fourier transform extracts from this function. It gives you these relative amplitudes. Okay? I'm going to probably skip through this, but you can think of Fourier transforms in the temporal domain such that if your function is a vibration by a speaker, say in time, then when you take the Fourier transform at a specific frequency, which is like 100 kilohertz, so you say, what's the power or the amplitude of the signal at 100 kilohertz, right? And what is it at 200 kilohertz, et cetera? And that gives you the Fourier spectrum of that sound, right? And so when you take a violin and you record it, that gives you a particular G of T. You take the Fourier transform of that thing, and that gives you a particular set of amplitudes at different frequencies and overtones that define what a violin is, right? For it's one way of defining it, right? You just look at those Fourier coefficients. Similarly, in space, same thing going on. If I look at a pattern in space of brightnesses, they oscillate in some way, and I take the Fourier transform with a particular oscillation in mind. At that point, I say, what's the power of the frequency at that point? And we saw in those plane waves, we would only have one frequency, right? When we took the Fourier transform of that thing, one frequency would pop out because that was all that was there, was that sine wave in the plane. So looking at a few Fourier transforms, these are particularly useful ones. If I take the Fourier transform of a delta function, so here's our input. This is our classic little dot input. I'm going to take the Fourier transform of that thing and say, well, what frequency components are contained inside the delta function to make this function that's all zeros and then really high and then all zeros again? What frequencies are there? Let's take the Fourier transform, we'll find out. Well, the delta function, as you recall, when we do this integral, right, it sifts out, the value, basically. And so if I, basically this thing here it has finite value only at one x location, right? We know that. So this integral is 0 unless x is 0, right? So it's going to sift out, you know, this thing at x equals 0. And so this whole thing comes to 0 and this goes to 1. And so that says that the Fourier transform of that spike, right, when I do that integral, it's basically for every spatial frequency, doesn't matter what I set kx, it's 1, right? So it's a constant. It has amplitude at all spatial frequencies. This is kind of a problem with this function, right? So I have a spike. And now you're telling me it's 1. It goes out to infinity at 1. So it has like an infinite amount of energy in it, right? So anyway, that's Fourier transform of a delta function. It's a straight line at 1. Fourier transform of a delta function that is shifted off the origin, same thing happens, right? It's only 0 when x is at x naught. And so this integral turns into this function, right? And it's simply a phasor that is oscillating at this frequency, right? Kx in the kx space, we have it oscillating in that space at this kx x naught is now our frequency. So that's essentially a phasor thing. We'll see a picture. The Fourier transform of a rectangle, we already told you the answer was going to be a sinc, right? So a rectangle, when you do the Fourier integral, well, you can cut out the minus infinity to infinity because you only have function between minus and a half to a half, right? So it's a finite integral of this function, and we know our function in here, f is 1. And so when you perform that integration and, you know, just do it like a finite integral, you get this, and that simplifies down to this function here. So it's sine pi kx over pi kx. So again, it's something that's oscillating, right, as a function of position in or in frequency space in k, and decaying away. So here's what it looks like. Here's the delta function at 0. Its Fourier transform is 1 everywhere, right? The delta function offset at x naught, it is a phasor that is oscillating as a function of that distance off. If I move this farther out, this oscillation happens at a higher frequency, right? And the rectangle function, its Fourier transform is this function, which is the sine wave, which is decaying away. Okay. We are done. So we'll stop there. We'll probably pick it up on Wednesday because there's basically these tables are things that you want to know, right? These transform pairs and the properties of the Fourier transform. So we'll review that when we go to Wednesday. Okay. Sorry about the mess up with the Wi-Fi.